Hi, this is Natalie. So in this video, we're going to explore the sampling distribution of the sample mean x bar. So the distribution of a statistic is called a sampling distribution. And today we're going to see a relative frequency distribution of various values of the sample mean using a number of samples. So first, we're going to see the central limit theorem. There are actually two circumstances under it. First, if x follows the non-normal distribution. Let's just consider a random sample of n observations selected from a population. Unlike the binomial, the Poisson, the uniform, it can be any population other than the normal population, with the mean of mu and the standard deviation of sigma. When n is sufficiently large, in our unit, it means the n is no less than 30. So the sampling distribution of x bar will be approximately normally distributed with mean of mu and standard deviation of sigma divided by the square root of n. So it can be written in this way. It means that x bar approximately follows the normal distribution of the mean of mu and the standard deviation of sigma divided by square root of n. And the second circumstance is that if the x it just follows the normal distribution, then x bar is normal regardless of the sample size. It can be either like smaller than 30 or larger than 30. It's just because the population itself follows the normal distribution. So you can see the difference here. This one is the approximately follows the normal distribution, but here it is exactly follows the normal distribution. So now let's see the statistics of the sampling distribution of x bar. The mean of it n equals to mu. In the variance, it equals to sigma squared divided by n. And the standard deviation equals to the sigma divided by square root of n. And the standard error. The standard error is just the same as the standard deviation of a statistic. So it's also just like this one. It equals to the sigma divided by square root of n. And now let's see this, how to standardize the sample mean. As the x bar follows the normal distribution with the mean of mu and the standard deviation of sigma divided by square root of n. So we can do just like what we have done before. We can see what x and what z follows. So z is actually using the x bar minus the mean, which is just mu, and divided by the standard deviation of x bar, which is the sigma divided by square root of n. And z follows the normal distribution with the mean of 0 and the standard deviation of 1. So let's see an example to illustrate this. The manufacturer of the cans of salmon that are supposed to have a net weight of 120 grams tells you that the net weight is actually a random variable with a mean of 121 grams and a standard deviation of 3.6 grams. Let's find the probability that the mean of a random sample of 36 cans is less than 119.4 grams. So let's solve this. Let x be the weight of a can. Though the distribution of x is unknown, but since we can see the sample size n equals to 36, we can now use the central limit theorem, just like this one. So we can see that the x bar follows the normal, it approximately follows the normal distribution with the mean of 121 and the standard deviation. We can see the variance of 3.6 squared divided by 36. So let's see the probability of x bar smaller than 119.4. So when we standardize it, we can get that it's equal to the probability of z smaller than minus 2.67. So let's calculate it. So it equals to the normal standard distribution, and the z equals to minus 2.67, and it's true. So this is what we have got.